Hi guys. Today we're gonna work through this problem, okay? So using the result from B2, derive an expression for the overall thermal resistance of a pipe of radius R1 wrapped with insulation of radius R2. So let's first draw the scenario, okay? So that's the inner radius, and then let's draw the outer radius. So inner radius is R1, and then outer radius is R2. So we know that there's uh there's heat flow and heat transfer. So there's two type of heat transfer in this problem. First is heat transfer by conduction from the inner metal, um from the hot inner metal out to the colder outer surface, because heat travel from a high temperature to cold temperature. And then there's heat by convection because of the surrounding environment, let's just say air. Okay. And so we determine in B2 that the thermal resistance of by conduction of a cylinder is natural log of R2 over R1 over 2 pi k times length. And then we know that R by convection is 1 over HA. So let's find the total thermal resistance. So R total is those two added together. And so we know that A, the flux area, the surface area is two, it's throughout the entire outer surface of the cylinder. So it's gonna be 2 pi times the outer radius R2 times length. So we're gonna plug it in down here. And then so this is where we have a problem. Um, we can determine the we wouldn't be able to determine the critical point or of the radius with just this, because heat transfer by conduction, if when the higher the radius, the greater the radius, the greater the thermal resistance by conduction, the lower the heat transfer. But on the other hand, for convection, the greater the radius, the lower the thermal resistance, the greater the heat transfer. So we need to therefore determine the maximum or the minimum or the critical point. So we can do this by using derivative, as we learned in calculus. So derivative of R total resistance over the change in R2 is equal to, so this one, let's rewrite this. It's going to be L into R2 minus ln R1. So derivative of ln R2 with respect to R2 is 1 over R2. And then minus derivative of ln R1 over R2 is 0, because R1 is a constant. Over, oh, and then we can also cross out this too. Wait, let's just factor 2 pi L out, because they're common factors. So 2 pi L over 1 R, and then 2 pi L is a constant anyways, over K time plus uh plus 1 over R2 square over 2 R2 square times H. And then, so when the derivative is 0, that point is going to be either the maximum or the minimum. So, and then we can also cancel out 2 pi L. So we can have um 1 over um 2 1 over R2K plus minus let me double check the math real quick. Uh, derivative 1 over X is what is the derivative of oh, sorry guys. I made a mathematical mistake. So this one should be -1. So yeah, I'm sorry about that. Minus 1 over R, this one's R2 H. Yeah, R2. And then we move R2 square H over to the other side. And then we divide both side by R2. So 1 over R2 H equal to 1 oh wait, I mean K over H, therefore R2 is equal to K over H. Get R2 equal K over H. We then at this point we know that this is the critical point, but we don't know if it's a minimum or the maximum. So we're gonna do the second derivative to determine that. Where R square is equal to um negative R squares K minus R2 square K minus or plus 2 over R2 to the cube H. And then we can plug R2 in because we know R2 is K over H is 1 over K over H square. Oh God, I don't have enough space. K over H cube. So we would have, let me just rewrite this entire thing over to the next page. So we would have 1 over -1 over K cube H equal to 2 over K cube H square. Oh, this one's also K cube X squared. So therefore we have 1 over K cube H square equal to H square over K cube. And so if the second derivative um is larger than 0, then the critical point is the minimum. And the curve's gonna be concave up. And then if it's less than 0, critical point is maximum, concave down. So we know that K is always positive because Fourier's law, negative Ka dt dx. If K is negative, then this entire thing would be positive. So what I would say in code, he goes from cold to heat to hot, which is not true. So K, we know K is always positive, and H is also positive. But regardless, since there's a square, they're all going to be positive anyway. So we know that second derivative of total resistance over with respect to change of radius 2 is positive. So that point R2 is going to be the minimum. Let's just say there's R1 over here and then R2. And then let's draw a curve. It's gonna have a parabola shape. And then to talk about more about the last question, since we know that the change in R2 has opposing effect on conduction and convection, we need to determine the minimum value. And then we know that if R is below the critical value, then we know that we're gonna have low resist high resistant or low resistant high heat transfer. And then if R is larger than greater than R critical, then we can have high resistant low heat transfer.